Good morning, student. Today we will discuss the A.C.Servo Motor. It is the one of the control system component. So A.C.Servo motors are used for low power applications because they are light in weight, rugged in construction, and there are no brush contacts to maintain. So A.C.Servo motor is also called as the two-phase induction type motor. Here in this case, the motor consists of the two stators winding. One is the fixed phase winding, another is the control phase winding. Through the fixed phase, we have to apply the fixed voltage to the stator winding, which is called as the fixed phase, and another is called the control phase. So under normal operating condition, fixed voltage from the constant voltage is applied to the one phase, and other phase, which is called as the control phase, is supplied by the voltage of variable magnitude and polarity. So if you change the polarity of this control phase voltage, then the direction of the motor will be changed. Okay, so the rotor construction is usually of the squirrel cage type, and the diameter of the rotor is made small in order to reduce the inertia. And if you reduce the diameter, then it will help in improving the acceleration characteristics. So this A.C.Servo motor is of two-phase induction type. This is the torque speed characteristics of the A.C.Servo motor. So it is well known that the shape of the torque speed characteristics of A.C.Servo motor. This is the torque speed characteristics of the conventional induction motor and the A.C.Servo motor. So the ratio of the rotor reactance to rotor resistance. On this ratio, the characteristics of the machine we can define. So characteristics of the machine depends on this ratio, that is a rotor reactance to rotor resistance. So for conventional induction motor, X by R ratio is very high. This is X by R ratio. So X by R ratio is very large for the conventional motors in order to obtain the high starting torque. Suppose large X by R ratio means by reducing the resistance, and therefore we can increase this large X by R ratio so that we can improve the maximum torque. However, this characteristic is not suitable for feedback control system because on some part of this curve there is a positive slope on the part of the curve. So the curve A shows that there are the positive slope for small portion, and that we do not require for the control system application. So next is, these are the torque speed characteristics for the different control voltages. We can see from this first figure the torque speed characteristics for the different control voltage. We can see that the A.C.Servo motors are rarely used for the higher speed. Okay, therefore it is generally operate at the lower speed, and we can see from the first diagram that the curves are linear for the lower speed, but it becomes non-linear for the higher speed, and therefore the what assumptions we have to make or approximations we have to consider that the resultant curves are should be parallel to each other. That means linear. We have to assume? We have to assume that the linear torque speed characteristics for the control system applications, and therefore for the lower speed it is obviously it is a linear characteristics, and therefore the K is the value we have to calculate from the block rotor torque. At this time the voltage, control phase voltage and the fixed phase voltage, they will be equal divided by the rated control voltage. So this will be the T0 by V1, and if M is the slope of the torque speed curve, and you know that the slope of the curve B is here negative. Slope of the curve B is here negative. That's why M is equal to minus block rotor torque divided by the no load speed. So minus T naught by N naught. So by taking the help of these two values, that is K and M, we can write the torque equation for the motor, that is Tm is equal to KV2 plus M into d theta M by dt. So this is equation number 1. And again, the motor is having the moment of inertia. The motor rotor is having moment of inertia Jm and the viscous friction Fm. If the moment of inertia and viscous friction for the motor rotor is considered, then we can write the equation number 2. Tm is equal to Jm d square theta by dt square plus Fm into d theta by dt. So these two torques are there. We have to equate these torques. If you equate this torque, we can write here kV2 plus m into d theta m by dt is equal to Jm d square theta by dt square plus Fm into d theta by dt. Taking the Laplace transform of this above equation, we can get k into v2 of s plus ms theta of s is equal to Jm s square theta of s plus Fms theta of s. So we will get the equation number 3, and we are interested here to find the transfer function. Okay, so the transfer function we have to obtain by taking the Laplace transform of the output variable to the Laplace transform of the input variable. Okay, so we have to solve the equation number 3 for this theta s by v2. So we have to just rearrange equation number 3, take v2 on one side and theta on one side, and therefore we can write this theta of s by v2 of s is equal to k over Jm into s square plus Fm into s minus Fms. So here we can take the Fm minus m, we can take s outside this, and so the second term in the denominator will be Fm minus m into s. And now we have to take Fm minus m outside the bracket. Hello. Oh, बोलो. तो खूप पुढे होता सर. पूर्वी होता तो मैं जरा भरने नहीं करती. त्या ऍडमिशन ऑफिस मध्ये असून नसतं आपल्याला करायचं. भरणे मी विचारणार त्याला. करायचं. हा, आणि आता सेकंड इयरला आपलाच होता ना. हा, मागच्या वर्षी समजा ते यांच्या क्लासमध्ये सगळं करायचं. ठीक आहे, ठीक आहे. हो. So this is the so we have to solve this for theta of s by v2 of s. This is km by s into tms plus 1. So this km is nothing but k over fm minus m. This is the value of km, and this is motor gain constant, and tm is the jm by fm minus m. This is motor time constant. So this is a transfer function for the AC servo motor. Thank you very much for watching the video.